one more video wrapping up wrapping up column buckling for what we need to cover in ME370. Several years past, I had actually had two different classes on buckling, and this is where we would introduce eccentric loading, right? And the real big problem that we have with eccentric loading, well, let me say, the real problem we have, the reason why eccentric loading causes a thing, first is the idealization for Euler buckling is that the load is exactly aligned with the center, right? If you go off center a little bit, what that's essentially doing is putting a moment onto the top of this right here, which is the thing like the fly in the ointment that's going to trip and cause buckling, right? So all of a sudden, by having this off center a little bit, we've like encouraged buckling to take place. Buckling is this sudden thing that happens where all of a sudden a fly lands on it, boom, and it buckles. But we're already adding the fly in there for eccentric loading. And I won't bother going through the derivation. Sometimes we call this the secant formula, and it's just the inverse of the tangent. I don't know, a secant shows up in there. You can see this E, that this is the eccentricity, right? That's the distance off from the neutral axis of where the load is being placed, which is actually probably kind of like real life, right? Like, why would necessarily the load always be exactly on center of the on the center line? It's kind of hard to achieve, right? So the real difficulty we have with trying to solve this problem, and you'll notice this is the yield and compression they decided to have, is that we have to find this P, we need this, it's inside here, right? So P, this load, this critical load, is in two places. And you have to ask yourself, well, how are you going to do that? Well, the answer is just to use a numerical method of some sort, or iteration, right? To be able to choose a P here, solve for this P. They're not going to be the same thing. Do it again, solve for it. What I would do, just as a kind of a cheat, right? Instead of trying to use some hard thing where you do it by hand, where I go back and forth, is I could put it in Excel and I could solve for, instead of these things, I could put these as inputs and I could solve for stress. I call it stress, but here it's strength. It's a number we know we want to do. So I have all of these arranged so that I'm solving for this, and then I just do a goal seek in Excel to drive this number by changing this P, right? And what that'll do is it'll just cycle through numbers until it gets to match there, and then I'll get the buckling information. So I think it's kind of interesting and informative to know about this eccentric load and the buckling, but also to see it put down on top as a graph, and you can see this, maybe this eccentricity ratio that they're calling it right here. So this is C, by the way. That's the distance from the neutral axis to the outside fiber, just like you would have MC over I. That's the same C. So you have eccentricity times that C divided by the radius of gyration squared. So the eccentricity ratio, you can kind of see this thing plotted out versus this unit load P over A, which also appears right in there, versus slenderness ratio, and we get various curves right here. And you can see if the eccentricity gets smaller and smaller, it starts to approach that Johnson curve right there. You can kind of see how that goes. This is the original Euler equation all the way up here. So this kind of also gives a little validation to how Johnson is. It's a pretty good thing. But you can also see where these sort of merge down to being closer to Euler's equation as you get further, as you get a higher and higher slenderness ratio. So as you get thinner and longer. But it's an important thing. Let me see, and I already talked about struts and short compression members. Let me go one thing. Let me pause this and find something. Find the FE equation book. So just 1 second. Okay, so in the Fundamentals of Engineering exam equation booklet that NECES provides when you take the FE exam, here's the mechanical engineering section. And if you come down a little ways, let's see, we have columns right here. All right, so right there, intermediate and long length columns. So one of the reasons why I include things or don't include them into the course is sort of the guidance of, well, how important was it to the people who write the Fundamentals of Engineering exam? Those are people who decided that this is important enough that someone who's a competent young engineer should know of, or should be able to maybe have a chance of solving this problem. So that's how they decide to include. So you could see, even though it's a little hidden right in here. Okay, no, there it is. For long columns, what this is here, they're going SR squared, which is, that's slenderness ratio, right? So they're defining SR right there as L over K, right? Where K is I squared of I over A, right? So there's your slenderness ratio, L over K, that we just talked about. And they're deciding this right here is the decision of should I or should I not use a long column or an intermediate column, right? This is the same thing as our equation, right, let's see, where did we go, right here. So this is the same thing as this equation right there. There's a 2 in there, and they got rid of C, but it's all the same thing. Right, there's the 2. They took the pi and they stick it out to the side right there. So if it's above this, you use a long column. If it's below this, you use an intermediate column. And you can see here's the intermediate column right here. So there's a critical buckling load, and these are all the same things that we've covered. They kept the slenderness ratio inside there, so that's important. And then for long columns, you can see this right here. That's the Euler Buckling, right? And I think for the L, they said L is the length of the column, but in this case, it's probably going to be the effective length right here. And there you go. And they said the effective length. Here's where they describe the effective length. So these are things that the people who created the FE exam think are important, and therefore should be included in an undergraduate mechanical engineering course. And ta-da! I have it included in the course, and so now you know why. So we're going to follow up with one last thing here, and that's other buckling, right? Other buckling. So there's column buckling, but that's not the only kind of buckling. And by the way, I should also point out, mechanical engineers might have this type of thing that happen instead of having columns, like, because not make bridges and towers and whatever, like we would have in civil engineering, but it might be like a part. Right? It could be like a linkage inside, like maybe a control system that would push and pull some other lever, right? You can picture that, right? Maybe a throttle or something. Some kind of, maybe some linkage part on a gas turbine blade control linkage or something, right? Okay, so something mechanical engineering, make it relevant to your life. And you might have to go through a long span and realize, boom, all the thing is going to buckle. Now, that's not as bad as column buckling. Column buckling is like people die, right? It could be supporting something that people are on or under, and people can die because of buckling, right? So buckling is an important thing to know about in the civil engineering. And mechanical, though, it's also something that could possibly be important. Now, did stuff on ships, right? So we had columns inside of ships to support between decks and that kind of thing. So we had to worry about it. But we also had local buckling and plate buckling. So this is actually there's other kinds of buckling besides just it being a column. And plates can buckle, and they can buckle in different shapes. And I should have actually mentioned this earlier on, probably in the first lecture of this series, where I talked about, like, where we got pi, right? And then we got 2 pi, we have 3 pi. Well, those actually are different mode shapes, right? So the first mode shape is this mode shape right there. That's the first buckling. The second one can be is usually going to look like a sine wave, and I'm messing this up right here. Let's see, like a sine wave right there. That's going to be the second mode that this thing could possibly, but it's never going to reach the second mode, but it's going to do the first mode. But you could perhaps put a guide wire right here in the center, right, that prevents the thing going in that way. So now it's actually acting kind of like two separate beams, two separate, like, in this case, pinned things on top of each other. It has split the thing in half. And that's how you can get the 2 pi solution instead of the single pi solution. So that's kind of like the concept behind here. But we have these are mode shapes, right? These other modes that this thing could possibly move in. And so for plate buckling, we have these kinds of interesting different shapes that a plate could buckle in, right? And it's not just this way and that way. You know, you can think of it as a column in this direction, it's a column in that direction, right? But you can actually have a twist in that kind of thing. There's other shapes. So cylinders can kind of have this like little, you could picture a tin can doesn't generally just squish perfectly. It almost there's one, it kind of goes to the side sometimes, right? So it's there's a local factor that can go into whether something buckles. And this local instability. So we actually, as mechanical engineers, when we were designing something, maybe the foundation for like a generator or something along those lines, you might want to consider, like if you're using, say, like a channel, right? So you're showing a channel right here, and you might run 2 channels, and you mount the generator and the engine onto these 2 channels, and then you have all the mounts that are holding the vibration mounts that are on the bottom of this thing. But where you drill through, like where the foot sits on top of the flange of the channel, that could buckle. So we put like little tiny brackets in between there. Sometimes we call those tripping brackets, right? So that because that's the phrase that the flange can trip, so that we can have these local buckling can take place. And that might be the mode that buckles first in terms of loading onto something. Like I think this one image is pretty important right there. If you had this flat plate that's just cantilever and sticking out, it might not fail in bending, right? It might fail by twisting and coming down out of plane. Designing is it's a field where you have to be like very much a pessimist and applying Murphy's Law and what's the worst thing that can happen, like looking for all the different possible things something can fail. And buckling is a really important one that can be overlooked when you're focused in on other areas of the design. It's one of those failure modes that can pop up when you least expect it. So that's what I had for buckling in this semester in ME370. I think it's enough information, but now you are aware of its existence.